For that purpose, I will start with refreshing you the basis of matrix method. Okay? The matrix method, you need to be very familiar with the procedures because it is very time consuming. Okay? Very time consuming. It takes a long time to solve using matrix method. Now the basis of matrix method is you need to form the structure stiffness matrix of the problems given to you, starting from the element stiffness matrix. So let me start with the basis of that, what you need to know. Okay? The matrix method, you need to know the basis equations that you need to know is these matrix equations. As on the left hand side is the structure nodal force plus E so here we have Q is the structure nodal force. Okay. But in our EAS663, we are not going to solve a problem with structure nodal force, but in general, what we cover can also be used to solve for a problem where you have a force applied. For example, in a beam column, and the delta here is the structure nodal displacement. Okay. So displacement at structure level, you can have translation, which is and rotation. Okay. So you have translation and rotation, two types of. So depending on the problem given to you, translation might be zero, rotation might be non-zero. We have to identify. And the K here, this is the normal stiffness matrix. Bending. So this is the normal one, which is encountered for loading causing bending. And the one that we need extra to consider effect of axial force is stiffness okay. And the P, of course, is the apply axial force. Is the axial force. So this is the basis of equations that we are going to use. And our main purpose is to use these equations and then to try to get the P critical. And in order to determine P critical, we use the criteria that we have seen many times and also in slope deflection equation method, okay, to determine P critical. Okay, you have to be clear. The criteria that we use is the determinant of this matrix the determinant of the matrix must be equal to 0. Yes. So from here we get P critical. So in order to solve, so the first thing that you need to know is how to get this structure stiffness matrix, this one plus P multiplied with K1 for the whole structure, starting from the element stiffness matrix, and then apply these conditions. And of course, next, the mathematics, how to get determinant. Okay. Determinant of a matrix is a very time-consuming calculations. 2 by 2 is still manageable. If it is 3 by 3, then it is almost impossible to do hand calculations. We need computer, we need calculator or program to help. But the basis procedure, you must be clear. Get this, and then only you can come to this part. And to get this, you must know how to get this big K from the small k. Okay. So the assemblage process is one thing that you need to go through in order to get to that big one, which is basically we try to combine all the K of element into the big K. So this process we have gone through where you need to do coordinate transformations. You need to do coordinate transformations in order to get to this big K. And this is also a very time-consuming process because there are a lot of matrix multiplications involved. So this is a bit of a review on the basis of this method, because later on you are going to go through many methods. If you're asked to use matrix method, what is the procedure? If you're asked to use slope deflection equation method, so what is the procedure? If you're asked to use method of neutral equilibrium, what is the procedures? Okay. And this K and this K1 will be given to you if the question asks use matrix method, so you will be given this matrix and this matrix. You don't have to memorize, so you can save some of the memory for other things. You don't have to memorize this. You need to know how to get this. And you need to know how to get this from this process. And this process involves coordinate transformations. Later, we are going to look at one example where you need to have coordinate transformations, how to get to this, and then applying this is mathematical and need to solve this. And if you have 2 by 2, if the nodal displacement at structure level, there are 2 which are non-zero, then you have matrix, the size is 2 column, 2 row, and the equation become quadratic. The equation to determine P critical, it become a quadratic equation. So you need to solve the quadratic equations, and the solution for P critical is the smaller one. Smaller, you have 2 answers, and take the smaller one, positive one, as the P critical. If the question has only one non-zero displacement, then this equation is only 1. So only one equation, so that is relatively easy to solve. But if you have 2 non-zero displacement, then this matrix, the size of this matrix will be 2 by 2. Then the equation for determinant will become quadratic equations. Okay, you have x, you have p squared inside. So next, I'm going to go through with you again the process of getting this K. We have started with one example last week. Okay, and today I'm trying to follow up with that example where we are going to see how to actually come to the finally this equation here. Okay. Now, after that, we are going to look at one equations where we apply again matrix method, where we go through the complete process of coordinate transformations, and then you can see what are the things that you need to do. And I remind you again, this is a very time-consuming process. Okay? So you must be clear what to do and how to do matrix multiplications. Matrix multiplications, okay? Because you need to do a lot of matrix multiplications. Okay? And make sure your pen have enough ink, because when you write, then suddenly the pen ink finish. So bring 2, 3, 4 pen. Bring more pen, okay, or pencil, okay, and make sure there's enough paper. But in the exam, you can ask for more papers. Yes. Okay. Okay. So now I would like to continue with the equation, the example that we have started. We have already obtained the structure stiffness matrix. And we will continue to look at that example, how to consider the support conditions. Okay? How to consider support condition is similar to what you have gone through in EAS663, the finite element method. You have to take away the column, take away the row. Okay? So this is a bit of looking back into that as well. Let's see where it is. Okay. So I have used this example in last week. And this example, as I mentioned, this is the problem that you are given to solve. This is the structure that we want to solve. Then if you want to use matrix method, then you divide them into, if you are given instructions, divide into 2, then you follow the instructions. Okay. If you are not given, then up to you. You want to divide into 2, 3, 4. The more you divide, then the calculation will become very long. Okay. So the minimum is 2. So this is the problem given, and this is the way we divide them into 2. Same thing like your finite element, divide into 2. And then next one, this one further split them into element. You split them into element. Okay. So at this element level, as I mentioned again, so here at this is structure level. So you have the structure nodal force is the W, is a symbol of W here, is the structure nodal force. That is where the vector Q is. And the structure nodal displacement, translation and rotations here are given by big delta here. So delta 1, delta 3, delta 5, these are all translations. Then delta 2, delta 3, delta 4, delta 6, these are all rotations. Okay. So these are the structure nodal displacement, and you have to identify. If later we are going to see if this is fixed, then which one becomes 0? Okay. If this is fixed, then which of the nodal displacement becomes 0? You have to get that from the problem given to you. If this is only fixed and this is free, so which one becomes 0? Which means which delta will become 0? because that will affect what we do next. Okay. Now, if you split to element level, then we are using different symbol because the matrix that will be given to you as a basis is for element level, and they are all the same for all elements. Okay. And element level, you are using also there are nodal forces represented by Q, the symbol Q. So you have Q1, Q2, Q3, Q4, Q5, Q6, Q7, Q8. So this is repeated for each element. So Q1 to Q4 is for here. Next, start with, after 4, start with 5, 5 to 8 is for next element. You have one more, then start with 9 until 12 will be the next one. And for displacement at element level, you have delta. So the same thing, delta 1 to delta 4 is for first element. Then delta 5 to delta 8 is for second element. If you have a third element, here, then it will be delta 9, 10, 11, 12 for the next one. Okay. And the important thing also is to know the positive directions of the displacement and all the forces. So positive directions is defined based on the coordinate axis that we use. So x is always in the direction of the member. So if you start from here, so this will start from 1, 2, 3, 4. If you start from here, then it becomes 5, 6, 7, 8, start from here. So your x will be pointing from here to there. And this one, the x is pointing from here to there. And then once you fix the x, then you can fix the y. So if x is like this, the y becomes like this. Okay? If your x is like this, then y will be like this. If your x like this, y will be like this. Now this is especially important when later I go through one example. You have one element like this, and then element like this, then element like this. They're oriented in different directions, so you need to know what is the x and what is the y for each element, because the directions of all these follow the coordinate at the element level. So if this is x, this will be y. This is x, this will be y. And the positive direction for displacement or the forces, Q and delta, or W and delta here, will be opposite to the y directions. So if our y is pointing like this, so this will become positive pointing in the opposite directions. Then rotation always clockwise. Rotation always clockwise. So this is one important thing to take note. Okay. So next, we are going to go to that part. So, okay. And in that particular equations at the global level, you don't see this thing. You don't see the element nodal displacement and element nodal force, because this information is included by coordinate transformations. Okay. So for here, this delta 1 is equal to which delta in the structure level? This delta 2 is equal to which at the structure level? So that information is already included when we do the coordinate transformations. Okay. So that is the problem that we have started. And there's one thing that I explained is there is no support. This member is floating in the air, is not supported yet. So the problem that we want to solve, it will be supported. So after we form from the element here to the structure stiffness equations, then we have to consider the support. Okay. So we are going to look at two particular cases of the support conditions and how do we consider them in this matrix method. Okay. So after this, I'm going to go to a detail of this, which is given in the book by charges. And after this, I'm going to show you the application of this method to this example. Okay, so this example is a frame example, and this example has member like this, of course, and another member in this way. Okay, and this is a problem given to us. There is a frame with this L. This is also L, and this EI, they're all the same. Okay, but then we first identify what is the degrees of freedom, what is the nodal displacement. So the nodal displacement here is, this is, later we go to this is unbraced frame. So this member can sway. This one can sway. Okay. At the same time, this one can rotate. Okay. So we have here, it can rotate. It can rotate. Okay. That is the structure displacement. This one it can rotate. This one it can rotate. At the same time, this and this can move. This one can move. This one also can move because this is unbraced frame. If we brace it, you prevent it from going laterally, then it will be zero. But this is in general unbraced frame, meaning that this frame can move here or move there, and the frame also can rotate at this joint here. Now, in this example, the translation of this point and the translation of this point are the same. This translation and this translation, they are the same. So there's only one displacement that we need to consider, which is delta 3, which is the same for this and for this. Okay. Then, to solve this, we use one element for each of these vertical. This one, how many elements we want to include is up to us. Okay, we can divide into 2 here, divide into 2, divide into 2. We can divide into 4, divide into 2, divide into 4 is up to us. So because we want to do hand calculations to make it simple, we divide this only into one element. This is element 1. This one also one element, element 2. This one also one element, element 3. Then each of the element has its nodal forces and also nodal displacement. So element 1 start from 1 to 4. Element 2 start the number for Q and delta start from 5 to 8. And element 3, the number for the Q and delta start from 10 to 12. 9 to 12. Okay. And these are all the positive directions. These are all the positive directions for the displacement and the rotations. Okay. Then we will also later, when I finish the previous example, to see how do we solve this. So here, in particular later when I show you the solution process, which is in the book, how do we relate this delta to this big delta? That is coordinate transformation. Okay? And we need to form that relationship, which you relate the small delta here to the big delta. Relate the element nodal displacement to the structure nodal displacement. Okay. So that is the thing that I'm going to do in the first part. Now let me come back to this. Okay. Now, in last week lectures, we have obtained this, which is given in the book. Okay, so you have to refer to the detailed explanation process in this book. Okay. And this one is in which chapter? Chapter 2. Okay. If you go to this matrix method. This is where the question is. To go to refer to this. Okay. Now we have formed the structure stiffness equation, structure stiffness matrix for each of the element. Right. Now this structure stiffness matrix. Okay. So class later you refer to this because this is a bit too small. Even I cannot see it properly. So this is the starting one, which is common for all elements. And by going through coordinate transformations, we get to the element stiffness matrix for each of the element which already transform. Okay. So this is for element 1. This is for element 2. We already transform it. Okay. Then we combine these two. You combine these two in order to form. Okay. This is the combinations of it. This is a combinations of the two element stiffness matrix. And when we combine them, you are going to get a structure stiffness matrix. Okay. So this is the final after combination. So this will be the K plus P K1 in the whiteboard there. So this will be the K plus P K1. Okay, so there's a negative in front, actual one. So now this is the one that we have discussed, and we have already shown how do we get this. So now this is for the problem where there is no support. There is no support. Okay? So we are going to look at two conditions. The first one is if the column is fixed at the top, fixed at the bottom. And the second one is if the column is hinged at the top and hinged at the column. The detailed explanations of some of the equations is given here. I'm going to show you the process of how to consider from here without any support conditions when you want to consider the support conditions. Okay. So what you will get after you consider support condition is this big matrix will be reduced. It will be reduced. Okay. Now you have six row, 6 column, because the structure displacement, there are totally 6. Now, some of these, when we consider fix or pin, they will become 0. So when they become, you apply that condition, this matrix size will become smaller. If the non-zero displacement, only 1 left, so you are left with only 1. The matrix, only size 1 matrix. The rest all you don't need to consider. You can delete them. If the degrees of freedom, the non-zero, after you consider the support conditions become 2 only, so from 6 by 6 matrix, it will become 2 by 2 matrix. Okay. So we will consider fixed column and hinge column. Okay. So how to consider that? I think the detailed one, how it becomes, is given here. I'm going to show you the detail to be given in that particular chapter of the book. Okay. Now, the problem that we have is we have delta 1, delta 2 here, delta 3, delta 4, delta 5, delta 6. Now, if it is if the column is fixed and fixed, okay, this is similar to your finite element method, how to consider support conditions. It's fixed and fixed, which means this is fixed, which means delta 1 equal to delta 2 equal to delta 5 equal to delta 6 equals 0. If this is fixed and this is fixed, means all this 0. Okay. And if we know that if it is fixed, okay, then the shape that it is going to buckle into will be like this. Okay, this is a buckle shape. If the column reach the P critical, the buckle shape will be like that, and meaning that at the center here, you have a slope 0 there. This is 0 slope. Because it's symmetry, then we have another extra condition, which is delta 4, 0. Okay. Delta 4, 0, because of these conditions here, which is, it is symmetry, and there is a 0 slope here. 0 slope means delta 4, 0. So this is, we additionally restrict that to the buckling mode that we know. Okay. So with this, the only non-zero become delta 3. The only non-zero will be delta 3. Okay. So this, the K matrix, which is originally 6 row and 6 column, okay, when you consider the support conditions, if you use the support conditions, so this K become very small. Only 1 and 1. Okay. From very big, become very small. 1. Okay. It will become smaller. The size is reduced. So here, if you want to relate to this, so this is delta 1, this is relate to delta 2, this is relate to delta 3. The original size of the matrix, okay? And the row also I can write in this way. So when you consider support conditions, so if delta 1, delta 2, delta 5, delta 6, 0, delta 4 also 0, so all this column, all the column which is related to delta 1, so you delete this one, delete it, delete, and also delete number 4. Okay, so when you delete the column, the row also is, you have to delete because the row is not helpful anymore. So this also you delete. Delete. This one means you take away. So that's why from the big one, so the only one left is here. So the K, that's why I write to you the K, the small K become big. The big one become like this, okay? Maybe the one, the other side cannot see, so. Okay. So there is only, okay, make it a bit bigger like this, okay? Only one row, one column. Because your non-zero displacement only 1. So once you have this only one, so both of this, this one and this one, both you have to take away the row and the column. So this one here, this one means including both of this, and then you have only one row and one column left, okay? And then one row and one column, then we want to apply determinant of this, which is one row, one column equal to 0 to get the P critical. So you have only one equation that you need to solve for P. So then, okay, after that, I go back to the notes there and show to you where is the equation that you need to solve. The second one is the pin. Pin and pin, okay? If pin and pin, meaning that pin here, pin delta 1, 0, delta 5, 0. Then we are interested in finding the P critical for the lowest buckling mode. So the lowest buckling mode will also be symmetry. Will also be symmetry. So we have a non-zero, a zero slope here. So again, delta 4 becomes 0. Okay. So in this case, 1, 2, 3 becomes 0. So the big K here, 6 by 6, will be, if you consider the support conditions, it will become 3 by 3. So this is a bit larger. 3, 3. Okay. Now, if you do 3, 3, so if I come back to this, so I come back to this here, it will become if we do the same thing for this case, so delta 1, 0, this also 0, okay. Delta 5, so row number 5, 0, delta 4, so as a result, we have only this part and this part remains, okay? So the actual K that we have to solve is a 3 by 3. Then we apply. So now this is the process that we have to go through in order to consider support conditions. So the second case, pin, if we consider this delta 1, delta 5, delta 4, 0, okay, meaning that we get into a 3 by 3 matrix of these structure stiffness equations. Okay, and to determine the P critical, you need to apply these conditions. So determinant of this equal to 0. So this become a cubic equations. So we find the equation, the smallest one will give us the P critical. So this procedure, I think, is if you can recall your finite element method, okay, it is similar. The way we consider support condition is take away the column where the displacement is 0, and if you take away the column, you take away also the row. Okay, because the row is not helpful anymore in the solution process. That's why you take away the row, so you reduce it to reduce the size. Now, this one we do it at the end. We form the structure stiffness matrix without considering support conditions. Then we apply the support conditions on the structure stiffness, then we reduce it. In the next example, I'm going to look at with you, we directly from the beginning consider the support conditions. So you can have two ways. In this example, right from the beginning, we don't consider any support conditions. We get the full structure stiffness equation, which is a 6 by 6. Then only we reduce it. Okay, then we solve. Another way is right from the beginning, you consider the support conditions. So where do you consider that? You consider it in coordinate transformations of the element stiffness matrix from the element coordinates to the global coordinates. So that one I will show you in the next example. Okay. So class, this is how we do it by consider support conditions. And the equations that we need to solve for the first one is only one equation because the non-zero displacement only one. Here, the equations, the size of the matrix, so the determinant of this 0, so this become a cubic equations. This is very difficult to solve. Okay. Then, because the non-zero one has 3. Now, later when I go through with you the particular chapters in the books that show you the detailed solution process of this, I hope you go through that. It further reduce this from 3 independent displacement to only 2. Okay. So that is the one that I'm going to show you where you can find that. So this is the basic idea of the process. Okay, so you need to know which one is 0 and what to do with the structure stiffness matrix, and only finally apply these conditions. The determinant of K becomes 0. Okay. Now, before I stop for a while, I think this is the class. I hope you refer to this. This part here. This particular page 140. So this is the fixed one. Okay. So the fixed one is left with only one equations because all are deleted. Left with only one equations. So in order to find the P critical, the stiffness must be 0. The determinant of that K0 means the stiffness, there is no stiffness. Okay. The meaning of these equations, this represents there is no stiffness. When the column is subjected to P critical, then the stiffness becomes 0, no stiffness. So here in the case of only one equation, directly we make this stiffness equal to 0, and we can solve for the P critical. And in this book, it compares with the exact one, so it is very close to the exact one. And the second case is we come up with these conditions, which is this one. This one is already considered at this particular page here. This one is where you already delete the column. You delete 3 column and 3 row. So we are left with 3 row and 3 column. You have to do the same thing for this one and this one, okay? Because this is divided into 2 parts. Do the same thing, delete the column, delete the row for this, and delete the column and delete the row for this as well. Then you ended up with this one. In this particular page here, it further reduces it into only 2 independent displacements. Why only 2? Because of the symmetry of the buckle shape. Symmetry of the buckle shape means, we go to that. Okay. You can stop here. You can stop here and then solve this, and then you get 3 solutions, and then you choose the lowest one. Or in that particular chapter there, in that particular page, it further uses the condition that this is symmetry. So the slope here and the slope here, they are equal in magnitude, but opposite in directions. So this is further one more conditions imposed because we are interested in the lowest mode. So we know that this is the lowest mode. So the slope here and the slope here will be the same. Okay. Slope here and the slope here will be the same, and they are in opposite directions. So in this case, another condition is being imposed. Okay. So this one is the slope here is delta 2. The slope here is delta 6. So delta 6 become negative delta 2. This is the condition of symmetry. Condition of symmetry. This and this rotations, they are the same magnitude, but this one is rotate clockwise, this one rotate anti-clockwise. So we have these conditions. So if we put additional these conditions, so the independent one become delta, and then delta 1, delta 2. So delta 2 and delta 3 only. Okay. If we impose these conditions, so we can further reduce the independent displacement into 2 only, which is delta 2 and delta 3, because originally delta 6 is here, but because delta 6 is equal to negative delta 2, so we have only 2 independent displacement. So further, the matrix is further reduced by size from 3 by 3 to 2 by 2. Okay. So this is what is shown in this example here. But if you don't do this, you can also solve this. Then you get the smallest one. But if you want to reduce it, because these are all hand calculation examples, so we further reduce it by imposing these conditions. This condition is a symmetry in the buckle shape. So our solution here can only have symmetry buckle shape. Can only have symmetry buckle shape. We don't have a non-symmetry buckle shape. So it is reduced to 2 by 2. When you reduce by 2 by 2, the hand calculation is still possible because 2 by 2 matrix, the determinant, you can determine the determinant. Okay. So that is what is being shown here. Here, this is, you can see here, please check the book. This is delta 6 equal to negative delta 2. Then here, how to get to this, you need to know the basis of matrix, matrix operations. From here, you can reduce to this one, which is 3 by 3 become 2 by 2. because of this is negative delta 2, so this column you have to plus to the delta 6 and delta 2. So this column you have to plus to the first column, and then you get this, and then the third row you don't need to consider. So you negative of this column plus to this, negative of this plus to this. Okay, then you can get, and then take away the third row because the independent one only 2, so we get to this. So how to get to this is actually you need to know some of the basis of matrix equations. So the basis here is negative of this column, you plus to this, negative of this column, you plus to this, and then take away the third row, which means you reduce the equation to only two equations and 2 unknowns. So you get to these equations. So the determinant of this must be equal to 0, and the rest is solving some of the, to make it easy, so they do some substitution for solving this. Okay, so finally you get the solution. Finally you get the solutions. This is still quadratic. This is still quadratic equations, and then take the lowest one. Okay. So class, if you refer to what I explained there and also refer to the notes here, it gives you the solution process of matrix method and how to consider the support conditions, and finally how to get to the structure stiffness matrix and apply the condition determinant of structure stiffness matrix must be 0 and solve. Let me take a short break here.